Namaste dosto. Imagine you're in a big room where you can walk forward, sideways, or even climb upstairs. To describe exactly where you are in this room, you need three numbers, right? This is what we call three-dimensional space. Just like on a flat map where you have x and y coordinates, in 3D each point is shown as an ordered triplet. That means three numbers written inside brackets, so like this. Open bracket x, y, z, close bracket. These numbers tell you how far you are along the x-axis, the y-axis, and the z-axis, which you can think of as going left-right, forward-backward, and up-down. Now, to have a common starting point, we use what's called the origin. That's simply the point with coordinates 0, 0, 0. This origin acts like the center of our 3D coordinate system. Every other point is described in relation to this origin. Also, the three main coordinate planes x, y, yz, and zx are like the walls and floor of your room. Each plane shows how two of the coordinates change while the third is fixed. Understanding these planes helps us figure out how points relate to each other in space. This foundation of representing points in 3D is essential because without it, calculating distances or angles between points would be very confusing. So, remember, every point in 3D space lives at a position determined by three numbers along the x, y, and z axis, all measured from the origin. Shabash. Let's keep this idea in mind as we move forward. Let's build on that and find out how to measure distance between 2 points in 3D space. You know how in 2D the distance between 2 points uses the Pythagorean theorem? We just extend that idea into the third dimension. Suppose we have 2 points, call them A and B. Point A is at coordinates x sub 1, y sub 1, z sub 1, and point B is at x sub 2, y sub 2, z sub 2. To find the straight line distance between A and B, we use a formula which is a direct extension of the 2D distance formula. Listen carefully to the formula. The distance AB equals the square root of, and now this is important, open bracket x2 minus x1 close bracket squared, plus open bracket y2 minus y1 close bracket squared, plus open bracket z2 minus z1 close bracket squared. Let me say that again slowly. Distance AB is equal to square root of the sum of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. This tells us the Euclidean distance, basically the shortest straight line path between the 2 points by accounting for the differences along all three coordinate directions. What's neat is that this distance doesn't change if we shift the whole space around, so it's a reliable way to talk about length and diagonals in 3 dimensions. Excellent, beta. Now you have the formula that unlocks distances in space beyond just a flat plane. To really feel this formula, imagine a box-like shape of a cuboid or where points A and B are on opposite corners. The distance we want is the diagonal stretching directly between these 2 points. If you think of this diagonal as the hypotenuse of a right-angled triangle, you can break the problem down. First, apply Pythagoras' theorem to the base of the cuboid in the xy plane to get a diagonal there. Then, think of that diagonal along with the height in the z direction, forming a right triangle in 3D space. By applying Pythagoras' theorem twice, or first to the horizontal plane, then including the vertical direction, we arrive at the full distance formula we just discussed, which involves the squares of differences along x, y, and z. In concept, this is like combining the squares of the projections of the segment on the xy, yz, and zx planes. This geometric understanding helps connect the numeric formula back to a shape you can visualize. Arey wah! That's the magic of extending 2D geometry into 3 dimensions. Now, let's see all this in action with a solved example. Suppose we want to find the distance between point A at coordinates 2, -1, 3, and point B at 4, 3, 1. Step 1. Calculate the difference along the x-axis. That is 4 minus 2, which equals 2. Squared. This becomes 4. Step 2. Along the y-axis, subtract the y-coordinates 3 minus -1, which is 3 plus 1 equal to 4. When squared, that is 16. Step 3. Along the z-axis, find 1 minus 3, which equals -2. Squared, this gives 4 again. Now, sum up these squared differences. 4 plus 16 plus 4 equals 24. Finally, the distance up is the square root of 24, which simplifies to 2 times the square root of 6. So the distance between points A and B is to root 6 units. If you imagine the 3D axis plotted with points A and B, you'd see this as the spatial separation forming a right triangle along each axis. Shabash. You just used the 3D distance formula perfectly. Here's a special, simpler case to remember. When one point is the origin 0, 0, 0, and the other point is P with coordinates x, y, z, finding the distance is easier. The formula becomes the distance OP equals the square root of x squared plus y squared plus z squared. This distance is actually the length or magnitude of the vector OP, which starts at the origin and ends at point P. You can think of it as the length of the arrow from the center out to that point in space. It's very useful for things like finding how far a point is from the center, checking whether points lie on a sphere of a certain radius, or simply measuring the shortest path from the origin to any point. Remember, this is a direct generalization of the two-dimensional vector length formula, now including the third axis. Excellent beta. It makes many problems much simpler. Let's quickly recap what we learned today. First, the formula to find the distance between any 2 points, A and B, in three-dimensional spaces. Square root of the sum of the squares of their coordinate differences, specifically the square root of open bracket x to minus x1 close bracket squared, plus open bracket y to minus y1 close bracket squared, plus open bracket z to minus z1 close bracket squared. Second, when one point is the origin O, the distance to a point P with coordinates x, y. Z is simply the square root of x squared plus y squared plus z squared. Third, geometrically, this distance is like the length of the diagonal of a cuboid defined by these points, extending Pythagoras' theorem into 3D space. In a sense, these distances capture the geometric length of segments in 3 dimensions, relate directly to vector magnitudes, another foundation for further studies in 3D geometry with applications in physics, engineering, and more. Soch ke dekho, every point in space has a coordinate that lets you measure how far it is from another point in the most precise way possible. Arey wah! Keep practicing these ideas, and you'll be ready to handle any 3D geometry problem in your exams. Shabash!